Right, so when last we left Bayes' theorem, which you'll see in lots of different ways written, like officially, really, even we often just put apostrophe after uh, the an S and leave it at that, and that's to become acceptable. Officially, it's supposed to have that annoying extra S, Bayes' theorem. So I will sometimes write it with one or the other or without anything at all. You'll sometimes just see it as plain old Bayes theorem, Bayes law, Bayes rule. They're not really typos, they're just alternate spellings, or they're typos that have become acceptable. So we had this monstrosity, which was the formula in terms of two events, E and F. Probability of E given F can be written as probability of F given E times probability of E, all divided by probability of F. And then we use this extra piece of information, law of total probability, to break it up as needed. And we want to see that in action in the real example. If you haven't seen the example of Massachusetts Democrats and Republicans support for the COVID relief bill, the $1.9 trillion package that passed in March 2021. Make sure to look at the version of it that was worked out using the tree diagram first, since that might make the most sense and not send your head spinning as much. But now I want to see it in same problem done, but using this formula that expresses Bayes' theorem as an equation. So I will not spend lots of time building from the basics. Again, I'm assuming you've seen this worked out once before a different way. We have Massachusetts voter enrollment by party. And well, I guess I'll show a little bit, right? So that was, as a reminder, the total number of Democrats divided by the total Democrats and Republicans. We'll call that the probability that I choose a Democrat, because I'm only going to look at Democratic and Republican voters. I'm not going to look at the unenrolled in a party. And so if I draw one of those from one of those buckets at random, if I draw from that set, probability that I get a Democrat is 0.765, probability Republican 0.235. And then I use this information from Politico from a poll at around the same time. Again, the assumption, if I'm going to use this, is that the breakdown among Democrats and Republicans in Massachusetts is the same as in the country at large. That's not strictly true. I mean, I'm using that information, treating as if this, in fact, we don't have information about Massachusetts specifically. So it is reasonable, if we're thinking about measuring our beliefs, to use what we have at the national level. If we think that Republicans and Democrats alike are going to be more supportive of the COVID bill in Massachusetts than elsewhere, you could use this information and adjust it a little bit upwards, or we can represent our uncertainty probabilistically. We're not going to do that here. We're just going to take this information as given. And so the probability that someone supports the bill, given that they're a Democrat in Massachusetts, or given that they're a Democrat in general, is 89%. So S is the event of support, and that means strongly or somewhat. And D is the event that the individual is a Democrat. Similarly, the probability of support given Republican is 60%, right? The sum of 34 and 26%. And so that's information that we have up front. And now the question is, if I choose a Massachusetts registered Republican or Democrat, voter at random, and I don't know whether they're a Republican or Democrat, I just know that I'm drawing at random from that, the general population of all of those Republican and Democrat voters. And if they turn out to be a supporter of the bill, right? So if it is now known that S is true, right? That S occurs, what is the probability that they're a Republican? Again, there's nothing random at this point about Republican or not Republican. I've chosen someone, it's fixed, right? It's not random, but it's unknown. And from the perspective of Bayesian reasoning, I'm updating my beliefs in light of evidence. So the evidence we have is what? It's that they support the bill. So that should give us potentially some information about the relative chances that they might be of one party or another. So we're looking for probability of Republican given support of the stimulus. We have the probability of the inverse, the transposed conditional. We don't want to just say, right, if you read this, if you got this on a homework problem in the future, and your instinct might be just to say 60%, but if you do that, you are committing the fallacy of transposed conditional, which is, specifically a specific form of that is the prosecutor's fallacy if it's in the legal setting. So let's match this up. How do we do probability of R given S? Well, I don't have a formula for R given S. I have a formula for H given E or E given F and so on. But the structure we need to think about, the structure is what matters here, not the individual letters. So when we have conditional in one direction and we want it in the other way, right? What do we have? Probability of R given S is equal to the probability of the flip, just like H given E, we flip it, E given H, right? Times the probability of the first one, R. And that numerator, again, remember, came from just how a conditional is expressed, right? The definition or the axiom that gives us conditional probability. The numerator is actually, the numerator itself just comes from rewriting probability of R and S, right? Or probability of S and R, which is the same thing. Probability of S given R times probability of R. And the denominator is what we're conditioning on. So we can, all of these, in the numerator, the pieces we have already, 0.235 and 0.60, right? Probability of S given R is 60%. Probability of R, probability that I pick a Republican, is 23.5%. Right, so I have that in as a product. Now, the problem is I don't have in my 4 bits of information up there, I don't have probability of S. I don't have the overall probability of support, right? If I draw someone at random from the population of Republicans and Democrats, what's the probability that they support the COVID stimulus bill? I don't have that. I have pieces of it that I can put together. That's where the law of total probability comes in. That's really the most complicated piece of certain versions of Bayes' theorem where you don't have that denominator already. Right, so what is probability of support? It's the probability that they support given that they're Republican, weighted by the probability they're Republican, plus the probability they support the stimulus given they're Democrat, weighted by the probability that they're Democrat, right? It's a kind of weighted average of the ways in which they could be supportive. They could be Republicans who are supportive, but that's a smaller share of the population. They could be Democrats who are supportive of the bill, but that's a larger part. And all of these pieces we have, right? So we already said the numerator is part of the sum and the denominator as well. We've already entered those figures, 0.60 and 0.235. And then we're adding it to the other side of the coin, the probability of support for the bill given Democrat, which is 0.89 times the probability of Democrat, probability that I selected a Democrat, 0.765, right? That works out to about 0.14 over 0.82 or 0.1716. That's 17%, a little bit more than 17%.